Okay, hi everyone. This is to explain the questions for hyperbolic functions in AQA MFP2 textbook. So let's look at the first one. Express cos x plus sin x in terms of e power x. So for this one, basically by using definition, it shouldn't be an issue for us to express it. So finally, at last, we actually get e power x, okay, by using the definition for cos x and sin x. For the second part, okay, is to evaluate the integral of this 1 over cos x plus sin x from 0 to infinity. So basically, this is just the same as integrating e to the power of negative x. And we just have to evaluate, okay, after we integrate the e power negative x, we get negative e power negative x, and we just have to evaluate this x at infinity, and x equals to 0. So when x approaches infinity, the value for negative e power negative x will actually approaches 0. So this is a curve for e power negative x. So when x approaches infinity, okay, so this value for the e power negative x will actually approaches 0. Okay, so after that we actually get this integral is equals to a 1. All right, so that's for the first question. The second question is, again, we have to use these definitions, okay, to prove for this identity where we have 2 sin x cos x is equal to sin 2x. So basically it's again, okay, by using the definition. So for the definition that we have here is for the sin x and the cos x, so basically we just have to expand them. So what we have for this is a part of the constants, we have got e power x minus e power negative x, to multiply with e power x plus e to the power negative x. So this one is some kind of the expansion which involves the a plus b, a minus b form. So at last we will get a squared minus b squared. Okay, so after we expand, we will actually find that, okay, the power of the e power x here is 2x and negative 2x. And then the sign is a negative. Okay, so for this one, we can actually change this to sin 2x. Okay, so that's for part A. So hence or otherwise, solve the equation where we have 8 sin x is equal to 3 sec x. So basically what we do is we just have to move the sec over. Okay, so we actually get a cos, okay, yeah, at our left hand side. And then the next step is we just have to apply the identity that we have proven from the previous part. So 8 sin x cos x can be written as 4 sin 2x, okay, based on what we have proven in the previous part. And now is to solve for the sin 2x. So the sin 2x, the value of the sin 2x is 3 over 4. So basically, how do we get the 2x is that we just have to use the definition for the arcsine. Okay, so this one can be obtained from our formula booklet. So basically just have to substitute the value of the 3 over 4, okay, into the formula given for the arcsine, and with that we can actually get a nice answer, okay, which is x is equals to half ln 2. Okay, so that's for the second question. The third question is by considering sin y is equals to x, okay, or otherwise prove that this is the identity, or rather the formula, okay, for arcsine x. So basically is they already asked us to consider this one as a starting, okay, so we will start with sin y is equals to x. So what happened, okay, for this proof is that, okay, we start with the definition for the sin y. Okay, so this is basically our definition for the sin y, and from there, okay, what we need to do is just have to try to form, okay, the quadratic equation which is in terms of the e power y. So in this case, our variable here is e power y, and from here we can actually use the quadratic formula to solve for our e power y. So from there, okay, for this part we apply, okay, the quadratic formula, and from there, okay, we'll actually have this simplified form, which is x plus minus root of x squared plus 1. Okay, so we cannot just take both values, because in this case we have e to the power of y, okay, if something is greater than 0. Okay, so this is what we know for the property for the exponent. So for this one, we can only take the positive value. Okay, so the plus minus, we can only take the positive value, and after that, just have to move the y, the the E over, and then we will actually get the ln. So this is why we get the arcsin x is given by this form. Okay, so this kind of the proof is something that we should be familiar with. Okay, so if you look at the next part of the question, okay, it says solve the equation where we have this, okay, 2 cos 2 theta minus 5 sin theta minus 8 is equals to 0. So leaving your answer in terms of the ln. So for this part, okay, what we need to do is we have to use a little bit of the identity, okay, where it is similar to the trigo identity, which involves a double angle. So what we have is we have a cos 2x, so we have to change it to something which is only in terms of theta. Okay, so for this one, okay, we can actually use the original identity. So we want to have something which is in terms of a sine squared. So if we start with this trigo version of this identity, we have got cos 2 theta is equal to 1 minus a sine squared theta. So this is a trigonometric version of the identity. So when we actually want to change this kind of the identity, okay, to the hyperbolic version, okay, we need to observe the Osborn rule. Okay, so what does this Osborn rule tells us is that whenever we have the square of the sine, okay, which we have a sine squared or cosecant squared or tangent squared, because they all involve the squares of the sine. So when we actually change it to the hyperbolic version, we need to negative it, or rather we say we change the sign. So what happens is that the cos 2 theta in this case, okay, is now 1 plus 2 sine squared theta. Because of the sine squared, we need to change this negative sign to be a positive sign. So this is where we actually get this identity, okay, in the hyperbolic version. So basically after that, the work is just make it into the quadratic equation, and then we can actually factorize them nicely. So we actually get two values for the sine theta, which we get negative 3 over 4 and also a 2. So from there, it is not difficult to continue from there. It's basically just apply what we have for the arcsine. Okay, so just apply this the ln form of this arcsine, and we can actually find the exact value accordingly. Okay, so just refer to the formula list for this. Right, next one. Show that the equation 14 sin x minus 10 cos x equals to 5 can be expressed into this exponential equation. So basically it's again by applying the definition. So just have to recall the definition for the cos x, because this is not given, so we have to remember this one. So cos x is the version that has a plus, the sin x is the version that has a negative. So we have e power x minus e power negative x. So basically just have to apply this, okay, into the equation. Basically the word after that is simplifying, and at some point we will get the terms which we have e power x and e power negative x. So usually we will actually change this to a quadratic equation by multiplying the whole equation again by e power x. So this is why we can actually get the equation that we need to prove. Okay, so after that is to solve this equation. So of course we know that instead of solving this equation in terms of the sine and the cos, since we already proven, okay, it can be written as something in terms of like quadratic equation, which is in terms of e power x. So we can actually make use of the quadratic equation to actually help us to solve it. So when we actually solve the quadratic equation, is very easy. Okay, we can factorize them nicely. We will get two values of the e power x in this case. So one of the values for the e power x is a negative value. So we are going to reject this value, or rather we say there's no solution to this, because e power x is always greater than 0. Okay, so this is a negative value. So basically there is no solution for this x. So for the other one, we have e power x is equals to 4. So we can actually get the value of the x very easily in this case, where we actually get x is equals to ln 4. Okay, so this is for the question 4. Question 5. Starting from the definition of a cos t in terms of a e power t, so show that we have got 4 cos cube t minus t cos t is equal to cos 3t. So basically the identity proving questions, they are actually very easily and quite straightforward. to show, okay, as long as we use the definition. So what is a difficult thing? The only difficult thing to do here is that because we have a cos power 3t, so it means we have to power 3 which is 1 over 2 and also e power t plus e to the power negative t. So this whole thing must power 3. So power 3, the 1 over 2, we get 1 over 8. And then for the exponent term, we have got e power t plus e power negative 3, e power negative t to the power of 3. Okay, we need to expand it carefully. Okay, so this is what we get after we expand it carefully. So basically the work after that is simplifying, okay, and we should be able to get something like this. So this the second last line here is something that we can actually write that in the cosh or shine. So for this case is a plus, so it will actually at last gives us a cosh 3t. Okay, so for the part 1 it's proving. Okay, for the second one, okay, we have got hence show that the substitution t equals to x equals to cos t, transform this equation into cos 3t is equals to 5 over 4. So why don't we just substitute this x equals to cos t into the equation and we will see what we have. So first, okay, we can actually do this equation. Okay, we can actually divide by 4. Okay, so you see like why do we have to do this? So after we divide by 4, okay, we actually have 4x cubed minus 3x. So the next step is to substitute the cos t in. So once we substitute this cos t in, we'll actually see that, okay, this is exactly the same as what we have proven in the earlier part. So just apply the identity that we have proven in the earlier part. So we actually get a nice value for the cos 3t, which is a 5 over 4. So from there, we just have to apply. This is again the ln form of the arccosh. Okay, so get it from the formula list. So with this, okay, we can actually get the value for the t here, okay, is equals to 1 over 3 ln 2, okay, by applying the ln form of this arccosh. Okay, so that will be for the finding the value for the t. So for this, okay, we actually have the part C. The above equation in x has only one real root. So obtain this root and give your answer in the form of 2 power p plus 2 power q. So p and q are rational numbers. So rational numbers are basically fractions. Okay, so with this, okay, what happened to the value of the x here is that we have to express it into 2 power something. So what happened here is because we have got this value of the t already, okay, we need to find out what is the value for the x in this case. So basically is to substitute the t back into the cosh, because again x is equals to a cosh t. So with this, okay, we just have to work with the expressions carefully. So this would be the values, okay, that becomes the power for the exponent term. Okay, so we just apply the definition for this carefully. And then how do we actually get to the next step is that because we have got e to the power of 1 over 3 ln 2 can be written as e power ln 2 to the power of 1 over 3. And we have this similar thing. Okay, and because we have got e power something, it's just equals to that term. Okay, so this is basically what we get. So this is how we get the second last line here. So basically after that, we just have to use this 1 over 2 to actually expand. Okay, so basically is to use, because this is also equals to 2 power negative 1, right? So you just have to multiply this 2 power negative 1 to the two terms inside the bracket and just work with the power, and we should be able to get the values for the p and q. So the p and q here, they are negative 2 over 3 and negative 4 over 3. Okay, so this is our question 5. So question 6, we have got the definitions for the sine theta and the cos theta. Show that we have tangent theta is given by this expression. So basically is again by using the definition. So you can see here, this is the sine theta and the cos theta definition. So of course we know that the half can cancel off. And how do you actually get the expression that we have, which we have e power 2 theta? So basically this can be easily done by multiplying both numerator and denominator by the e power theta. Okay, so with this we can actually prove what we want to show. Okay, so next is to prove that we have got the arctangent arctan, okay, of x is equal to this expression. So basically this is to start with the x is equals to tan theta, and then we know that the tan theta can be written as this one, okay, as the exponent form. So basically after that is to rearrange. So this is a bunch of the rearranging work. Okay, so it shouldn't be difficult for us to rearrange this. So we actually end up with the theta, okay, is given by this definition. So at last, okay, because we have got x is equals to tan theta, so in this case the theta here is equals to the arctan of the x. So this is why we get the expression that we want to show. So make sure we know how to do this. Okay, so we will look at the next one now. So next one is to express tan x in terms of a sine x and a cos x to show that we have got two things. The first thing is to show that the tan squared, okay, x is equals to 1 minus sec squared x. So in this case, the tan squared x can be written as sine squared over cos squared. So how do we actually get two terms here is by using the identity for the sine squared. So in this case, the sine squared is equals to cos squared x minus 1. Okay, so for this identity in the hyperbolic version is cos squared x minus sine squared x is equals to 1. Okay, so this is a hyperbolic version of this identity. So after this is by using the numerator, okay, which we have cos squared x minus 1 to divide. So we split the terms and divide. So this is how we actually get this 1 minus sec squared x in this case. Okay, so that will be the first part. The second part is to differentiate, okay, tan x, and we actually get a sec squared x. So this result is also very similar to the trigo version. Okay, so what can we do here is because they ask us to express the tan x into the sine and cos. So we do that, and then because this is a quotient, so we have to use a quotient rule. So when we use a quotient rule, that will be v u prime minus v u prime divided by v squared. So differentiating in this case the sine x is not difficult. We'll get a cos x. So this is why we get a cos square x as the first term. Differentiate a cos x gives us a sine x. Okay, so this is why we get sine square x here. So after that, this one in the numerator, we know that from the identity this is equals to 1. Okay, and we have got cos squared x in the denominator, so we just have to move it up and we will actually get this result, which is sec squared x. Alright, so second part, okay, is to find to integrate tan x minus tan power 3x. So for this one, okay, we need to do a little bit of thing that even if we see this kind of the expression in trigo, okay, the usual tangent, okay, we know that we are going to make it into something that is easier for us to integrate by changing it with some other identities. So for this case, okay, what we have is we can actually first factorize out the tan x. Okay, so why is it so important for us to actually factorize this out is because we want to have 1 minus tan squared. So 1 minus tan squared, okay, from the identity in the hyperbolic version, we'll actually have a sec squared. Okay, so for this sec square, okay, it actually helps us in the integration. So what happens is that we can actually use the substitution, which we have u is equal to tan x. So okay, why do we know we need to use substitution is that usually when we have we need to use substitution, the integral will usually appear as a product, where if we differentiate one of the term, we will actually get another term. So in this case, we know that when we differentiate tan, we will get a sec squared. Okay, so for this one, we know we are going to use the substitution. Okay, so we use the substitution again. Okay, u is equal to tan x. So it gives us that du is equal to sec square x. So integrating this thing, okay, the tan sec square after we replace everything by u, so it is just a u. Okay, so integrating a u gives us a half u squared. So after that, just remember to substitute, okay, our u into the u, which is tan x. So we get half tan squared x plus a constant. So this is what we get from the integration. Okay, so this is for the first part. So for the second part, okay, the question asks us to integrate only the tan cube x. So what happened to this one is that we actually have to use the result in the first part. So because in the first part we have integrated the left hand side, okay, which is this thing. This is what we have integrated, and we have already know the result. Okay, so now what we want now is we only want to find the result for this one alone, which is integrate tangent tan cube x. Okay, so just do a little bit of rearranging. So what we actually end up is that we will have to integrate this one. So integrate tan x. So integrating tan x can be easily done by writing the tan x into sine and cos. So writing this sine and cos is for us to integrate this, okay, into the ln form. So we actually have a ln of cos x. Okay, so with this, we actually get this result to integrate the tan cube x easily. Okay, so can look at the next question. So first question here, explain by means of sketch why the numbers of distinct values of x satisfying the equation cos x is equals to k in the cases of k less than 1, k equals to 1, and k greater than 1 are 0, 1, and 2 respectively. So what we have is, how do we actually look at this equation is we can actually look at it as two separate curves. So we have y is equal to cos x and y is equal to k. So we are looking at the intersection between these two curves. So they ask us to sketch. So we have got two curves here. So for this curve is a y is equal to cos x. Okay, and then what we have for the y is equal to k, it is just a horizontal line, okay, with different values for the y. So because we know that for this cos x, the value here, the minimum value that we have here is a 1. Okay, so with this we can easily use three different cases for the k, okay, in order for us to show that in these three cases there is 0 intersection. So for this one we have 1 intersection. For this one we actually have 2 intersection. Okay, so this can be easily shown by doing some sketching. Okay, so just have to remember that for the cos x graph, the graph is just like a quadratic curve. Okay, so that would be the first part. Okay, so for the second part, okay, part B. So given that cos x is equal to 1708 and sin y is equal to 4/3. So first is to express y in the form of a ln n. So n is an integer. So because the y comes from the sin y, so what we need to do is the y is just the arcsine of 4/3. So this one is not difficult to do. We just have to use, okay, the ln form of the arcsine, and we are actually able to get this value nicely. Okay, so that's for our y. Okay, so next, show that one possible values for x plus y is ln 12 and find the other possible values in the form of a ln a. So okay, so actually what happened in this case is that we have got, okay, from what we have from the sin y is that we have one value of the y. Okay, so in this case, our y value is the ln 3. So if you actually look at the question in the second part, it says that there is one possible value, which is ln 12, and there is another possible value. So in this case, how do we actually get the values for the x plus y is that for this x value from the cos x, okay, it must have two values. So in fact, we have already shown in the earlier part, in the part A. So because 17/8 is greater than 1. Okay, so what we have shown in the first part is that the x here must have two values. So from the symmetry property of this cos x, okay, this x value can take plus or minus, okay, of the value. So how do we get the x value is that? So for this one, the x value is a plus minus, okay, because remember from what we have sketched earlier on, this cos has two values. So just use the log form, okay, of the arc cos. So we know that this x is a plus minus arc cos of 17/8. Okay, so for this one, we actually get the x value here is a plus minus ln 4. So for the first value, okay, of the x plus y is by using the y is equals to the y is equals to ln 3, and we have the x is a positive ln 4. Okay, so this is how we get the first value, which is x plus y equals to ln 12. So we use another value for the x, which is the negative of a ln 4. So with that, we can actually get this another value for the x plus y, which is a ln 3/4. So this is what they mean by the A, okay, in the question. Okay, so we have got two values for the x in this case to give us two values for the x plus y. Alright, so let's look at the next one. So A, state the values of x for which arc cos x is defined. So for this one, arc cos x is defined when we have x is greater or equals to 1. Okay, so because remember we have the properties for the cos x. So if what we have, if in this case is we have the fx, okay, let's say we have the fx is equals to cos x. So the range of the fx is greater or equals to 1. Okay, we just seen the value for the cos x, right? So it will actually take the values 1 and above for our fx. So if we have the f inverse, okay, is equals to arc cos x in this case, so the range will become the domain. Okay, so the domain here will be x is greater or equals to 1, so which is the range of the values of the x for which arc cos x can take. Okay, so for this kind of the things is we need to understand the properties for the curves for the especially for the sine and the cos and their inverses. Okay. Part B, a curve C is defined for these values, okay, of x. So in this equation, the x will only take the value greater, which is greater or equals to 1. So y is equals to x minus arc cos x. So in the first part is to show that C has only one stationary point. So for this one, okay, we are going to differentiate the x. So we get a 1. Differentiating arc cos x is not difficult. In fact, we can actually just quote this from the formula list. Okay, it is already given. We don't even have to memorize it. So just quote the result from the formula list. And because we want to find the stationary point, so we make dy dx equals to 0, and we try to solve the x from there. Okay, so because remember this is a quadratic equation, so we may actually give the values of the x. Okay, at first we must give two values of the x, okay, which we get plus minus root 2. Then only we say, okay, because we already say the x is greater or equals to 1, we can only take the value of the x, which is root 2. So there is only one value of x, which means we have only one stationary point. Okay, so this is what we get from the first part. So for part 2, evaluate y at the stationary point. So find your answer in the form of a p minus ln q. So basically is to substitute this x into our function y again. So our y is x minus arcos x. So just substitute this x into the x and arcos x. So for this arcos x again, okay, we just have to use the ln form of the arcos. Okay, and then we just have to evaluate it, and we actually get this value of the y in the exact form. Okay, so we'll look at the next question now. Okay, so for the next question is to prove differentiate tan x is equal to sec square x. So this one we have already done it in the previous question. Okay, so we will skip this for now. So part B, hence or otherwise prove that arctan x is equal to 1 over 1 minus x squared. So for this one, let's say we just make this as the u. Okay, so we are supposed to prove that the du dx in this case is 1 over 1 minus x squared. So this is what we're supposed to prove. Okay, so what we do is we just let u to be arctan x. So it is easier for us to look at it from another way around, which we make x as the tan u. So next thing what we do is, okay, it is easier for us to differentiate the x. Okay, so we differentiate the whole equation with respect to x in this case. So of course, differentiating x, we get a 1. And now we have to differentiate the tan u with respect to x. So to differentiate this one, we know that to differentiate tan u, we get a sec square u, which we have proven in the previous part. And because we are differentiating, which is something in terms of u, but with respect to x, so we have to add a du dx term from there. So remember what we wanted to find is we want to find, okay, the du dx. So we just have to move the sec square over. Okay, then we will get 1 over sec square u. So again, okay, the sec square u, we can actually relate it, okay, with the identity. So the sec square u can be written as 1 minus tan squared u, because at last what we want to get is an expression which is only in terms of x, and our x is a tan u. So we have to relate back, okay, this sec with the tan, so in order for us to write it in terms of x. So from there, okay, because du dx is the same as to differentiate this arctan, and the right hand side, like we say, the tan squared u is the x squared. Okay, so from there we have already proven our second part. So for the third part, part C, by expressing 1 over 1 minus x squared in partial fraction and integrating, so show that arctan x is equal to this half ln 1 plus x over 1 minus x. So this result, okay, is obtained, okay, actually by using the second part. So basically what we need to do is we need to integrate both sides. So the first part, okay, the left hand side here will actually become only arctan. So arctan can be written as integrate the 1 over 1 minus x squared. So basically what we need to do is we just have to find out, okay, what is a partial fraction for 1 over 1 minus x squared, which is given by this form. And after we integrate this one, right, we actually have half, okay, and 2 long terms. So just have to be careful, like a lot of times, right, there's one mistake that we always do is that if we have a negative x, after we integrate, it will actually gives us a negative. Because when we actually integrate 1 over ax plus b, right, we will actually get 1 over a ln of ax plus b. So in this case, the a here is a negative 1. So we actually have 1 over negative 1, which will actually gives us a negative. Okay, so just take note of this negative. It is always one mistake that we always will do. Okay, so also remember that because we do not have definite integral, we have indefinite integral in this case, so we still have a c. Okay, so how do we actually deal with this c is that by looking at the value of the x and the arctan. So in this case, when we have x is equals to 0, okay, the value for the arctan is also a 0. So when we actually substitute into the integral, okay, what we have is we also have the c is equals to 0. So with that, it completes, okay, our proof where we have arctan x is equals to this long form. Okay, so we cannot just give our integral from this step to the next step without the c. Okay, it is not complete because there is no limits, okay, in the integral. So we have to think of how do we actually get rid of the c. So the way is by using this. Okay, so we cannot just stop here without giving the c. So it is not logical at all. Okay, so this is a thing that we have to take note. Now, if you look at the next one, so show that we have integrate this arctan x divided by 1 minus x squared is given by this a ln b the whole thing squared with 0 to 1 over 2 as the limits. So for this one, right? So okay, what can we see that is we have got something which is very similar in the previous part. So we know that we have differentiate the arctan x is equals to 1 over 1 minus x squared. So in the integral, we have got arctan, and also we have 1 over 1 minus x squared. So for this one, we know that we can actually use the by parts to actually find this integral. So it's quite an interesting question. So what we need to do is to split, okay, the arctan and the 1 minus x squared, because we are going to use a by parts. So we are supposed to integrate one of the term and differentiate another one. So of course, when we choose the differentiation in the integration, it's very obvious because it is easier to differentiate arctan because we have already know what is the result, which is 1 over 1 minus x squared. And we know the result of integrating 1 over 1 minus x squared, okay, because we have already proven that earlier on. So the result is arctan x. Okay, so it is actually quite easy to do. So this is the by part, okay, we just have to put all the results together. So this one is our UV. So it appears that our UV is an arctan, the whole thing squared. So of course we have to evaluate this at the limits lah. So we have got half and 0 that we have to evaluate. Okay, and for the VDU, okay, so for this VDU, when we actually multiply the V and the DU together, we will see that it is exactly the same as what we wanted to integrate at first. Okay, so what we need to do is for this term, okay, we just have to move it there. So we have got a 2. Okay, so for the right hand side here is just about evaluating, okay, the values for the arctan. So the arctan half, okay, is given by this form, okay, and for this arctan 0 is of course a 0 lah. Okay, so why do we have this half here is because we have moved this 2 over. Okay, so we have got 1 over 2. So how do we actually evaluate this arctan is in the question itself, it is already helping us. So we use this result, okay, to help us to evaluate the arctan half. So we don't even have to flip to the formula booklet. So basically, after evaluating everything, okay, we should be able to get a nice value, which we get in this case the 1 over 8 ln 3 the whole thing squared, which is the form that is required in the question. Okay. So the last question that we will look at is we have got this curve y is equal to sin x, and we have got AB is perpendicular to the x-axis. So first, given that AB is 4 over 3, so show that OB is equal to ln 3. So if you know that here in this case the value for the AB is 4 over 3, so it means the y value at this point is 4 over 3. Okay, so what we need to do is we just have to find out what is the x value for this, because the OB is just the value of the x in this case. So basically it's knowing that when we have y is equals to 4 over 3, so we know that the sin x is a 4 over 3. So basically is the x is just arcsine of 4 over 3. So basically what we do is we just have to apply the long form again. So if it actually gives us the value for the x, which is the same as the OB. Okay, in fact, is to show OB is equals to ln 3. Okay, next one, part B1. Show that cos of ln k is equals to this expression. So to show this, okay, we'll actually have to use the definition for the cos. Okay, so by using the definition of the cos, we will see that the powers, okay, are ln k and negative ln k. So just have to remember that if we have e to the power of ln of something, so it is just that something. Okay, so for this case, for e to the power of negative ln k, so for this one, you can actually write that as 1 over e to the power of ln k, which in this case, will actually gives 1 over k. So the next step is obtained when we actually tidy up the terms which we have the k and 1 over k together. We just add them together, make them into a single fraction. Okay, so this is what we do to prove for part 1. Okay, part 2. Show that the area of this region is 2 over 3. So it is not difficult at all. We just have to integrate the curve, which is shine, from 0 to x. Okay, the x that we have found earlier, which is we know is ln 3. So basically is to integrate this, okay, function shine x from 0 to ln 3. So we will actually get the cos x, which we have to evaluate it at ln 3 and 0. So for the first one, when we actually evaluate the ln 3, we don't even have to rewrite the definition again because the result is already given earlier on. So we can actually use the result for cos ln k. So just replace the 3, okay, into the k here, so we can get the term already. Okay, so cos 0, we know that is a 1. So by that, we can actually find out what is the area for this. Okay, is 2 over 3, which we are supposed to prove from the question. Okay, so for part C, so show that sine square x, when we integrate from 0 to ln 3, it actually gives us 1 over 4 sine ln 9 minus ln 9. So if you actually see this, okay, in order for us to integrate a sine square, so we cannot just integrate be it trigo. So we cannot integrate sine square and cos square, or even hyperbolic. Okay, we cannot just integrate the squares of the sine and the cos. So we have to make use of the identity. Okay, so a lot of times we will actually use the double angle, but it is in the hyperbolic version. So in the hyperbolic version, we have got the cos 2x is equals to 1 plus 2 sine squared x. Okay, so this identity we have used this, okay, in the earlier question. So the idea is the same. So the sine squared x, okay, can be written as this form. Okay, so with this, we can actually integrate very easily already lah. So cos 2x, okay, after integrate, we get a half sine 2x. So the constant become 1 over 4. And for 1 over 2, we get 1 over 2x lah after we integrate. So basically, after that is to sub this ln 3 and 0 and evaluate. Okay, so when x equals to 0, both terms here gives us a 0. So there's nothing there. Okay, so what we do is we factorize out the 1 over 4. So the 1 over 2 here becomes a 2. And we have got, inside the sine, we have got 2 ln 3. So for this 2, for the ln, we can actually move this 2 to become the power of the 3. So we get 3 squared. So this is why we have got the ln 9 in our expression. Okay, so that would be for the first part. The second part is to hence, okay, find to 3 significant figures, the volume when it is rotated 2 pi across about the x-axis. So this is to integrate pi y squared dx. So our y squared here is a sine x. So in fact, this integral, we have already found it earlier on. So basically, we just have to use the previous integral that we have and multiply with a pi. Okay, so basically for this one, we just have to use a calculator and we actually evaluate what is the value for this integral. Okay, so we actually get 1.76, which is rounded to 3 SF as required in the question. Right, so that's it for the questions, which is about the hyperbolic function. Okay.